right, on this lovely day, what we're going to be doing is understanding and using what's called exponential. And actually, I should change that. It's exponential, which are either growth or decay functions. So exponential is the description of all of them, and the two subcategories are growth and decay functions. So by way of review, linear functions show an additive pattern. That is, I'm adding 10 each time or adding $12 each time. And it always takes the form, or can always take the form, mx plus b. So for example, C of W is equal to 5501. W minus 372 describes the cost, C, of a diamond ring with a weight W in carats. In this context, this means $5,501 per carat. If you want one more diamond with one more carat, that's going to be another $5,500, please. Thank you very much. Exponential functions today. And notice up here, in a linear function, we have an additive pattern of change. This one adds $5,500 for every carat. But what if something doesn't grow in this manner? What if it grows by multiplication? So that's what this one would be here, multiplicative. So it's a multiplicative pattern of change. It multiplies by itself over and over and over again. And it will take a different form. So not y equals mx plus b like you're familiar with, but it's going to take what looks more simple, but this explodes significantly. So we have a b to the x power. So notice that x is in the exponent. And on top of that, if you wanted to undo this one, you have to use something called, we're not going to talk about it here, but you have to do logs, right? So this is how you undo, this is how you inverse exponential functions. So eventually what we're going to get to in the coming days is we're going to be using exponential reg. So we're going to be finding, instead of a linear line of regression, we're going to find an exponent model of regression. All right, so a has to be greater than 0. Because if a was 0, everything would just drop out and you would have just a constant. And A represents the original amount, usually. And we'll talk about that. Like if it was the original amount of, the original population of people, and we have a particular growth that occurs, a 2% growth of the population, what's the population going to be like in 10 or 15 years? Or the principal amount. How much money do you deposit in your account? Oh, I put $10,000 in an account, and I get a 10% interest, something like that. Notice that B has to be greater than 0. B has to be greater than 0. B is not negative. B cannot be 1. If B is 1, then so is all this, because 1 to any power is 1. So then again, you just get a line. And B represents the growth. Now, technically, not simply the growth. We call it the growth factor. But it could also be, when you talk about growth, you could also be shrinking, and that would be a decay. So our first thing we're going to do is just walk through and how to make the model. So we're not going to use technology. We're just going to substitute stuff in. So let's look at this. Presently, the towns of Scarsdale and Ambledon both have approximately 8,500 residents, which is twice as much as we have here, almost. So over the next 5 years, the population of Ambledon is expected to increase by approximately 2.3% per year, while the population of Scarsdale is expected to decrease by about 0.9% each year. So first off, let's notice that this one's increasing, and second, this one is decreasing. So how do we interpret this? Since we have an increase of 2.3%, remember how percents work, folks? That means your B is going to be this, 1.023. Anyone have any clue where that came from? So the 100% represents the original amount. And this part right here says original amount, add a percentage to it. Now, what's my A? In this case, A is going to be 8,500. So that's just my original amount. So if I want to talk about what the population of Ambleton is, I will say A of... All right, so we can use any letter here. I'm going to use P for people. And Ambleton population. So in this case is, I say 8,500. Times parentheses 1.023 raised to the power of, in this case, P. Now, of course, your whatever variable you chose. Good, so I probably want to change that from P to a T for time. So let me just change that real quick there. T there, and change that to T. T for time and being years. Now, what's the other one? Since we have a decrease, the 0.9% dropping down is like saying 100% minus 9%. So we're going to say this, that the population of Scarsdale after time T is going to be, it starts off the same with the original amount. And this time we're going to say 0.991 to the power of T. There are two ways to accomplish this. You can do this by hand and just say that 5 years and just plug in 5 here and 5 here and do that. Or you could put these functions into your calculator and just evaluate it that way. Whichever you would like put this in as a function, y1, and this one is y2. If we evaluate these at 5, so that means the population of Ambleton at 5 is going to be 8,500 times 1.023 to the 5th power. Just plug that in. All right, so when I plug this in, and I'm going to say an approximate value because, and I'm going to round this to up 1, so 9,524 population. Now, clearly we see it's a population growth. So in 5 years, it's growing quite a bit. The town growing quite a bit. Now, the other one is almost the exact same, but S, jolly, that's an S, right? S of 5, sorry about that, it's going to be 8,500, but this time we're going to put 0.991 to the 5th power to get an approximate value here. 8,124 or 25, but I rounded down to 24 there. And now from here, we can make a simple decision if he wants to make a significant amount more money. Look at this, nearly a $1,400 exactly difference, then he should invest the money with a CD as opposed to just putting it into a savings account. Jonas, if he's Czech. Yeah, that's how they pronounce it if you're from the Czech Republic. But Jonas, if you're that guy from that one band. Received a letter from his credit union stating that after a 5-year CD his parents opened for him had matured, and he had to could choose one of these options. Number 1, he just takes the money out and does whatever he wants with it, spends it or whatever. Number 2, he uses the money to open a new CD, and this one gives us an APY of 2.8%, 2.81%. Okay, so that's the growth per year. So it doesn't touch it, he just puts it in, and whether or not this is the rate of the old one or not, we don't know. We do know that's the rate of the new. Or you could have the money deposited in an interest checking account, which is less than 1% a year. Okay, so assume that Jonas's parents deposited $12,000 in the CD 5 years ago. So what's the equation for the balance of the old? So we want to get from here to here. And how do we accomplish that? Let's walk through and I'll show you on the TI real quick. So after we enter in the 2 points, 0 and 12,000, and we enter 5 and the 14, no parentheses, no comma there, 204.1 into L1 and L2. Then we're going to stat, calc, and what we did from there was exponential reg. In other words, not a line of regression, but an exponential function of regression. And this is what we end up getting. $12,000 is the original amount, also sometimes called the principal. My rate, according to my calculator, looks something like this, which interprets as a 3.43% growth. Now to answer this part here, use the equation from part A to find the annual yield. Just to give you a heads up what the annual yield is, that's what APY means, the annual percentage yield, okay? So part A, this is the equation for A. Part B says 3.43% annually. So you get nearly 3.5% of whatever's in there. And by the way, this is you doing nothing. You're not working. All you're doing is putting your money somewhere and letting your money work for you. So I highly encourage you to invest your money rather than just letting it sit somewhere.
Where did you get that?
Now the last part here. We're going to compare the results if he chooses to use this 2.81 and for the other one there. So let's see here. The function there will be, so in comparing options 2 and 3, what we're going to do is take the 14,000 and either let it grow 0.95% each year or let it grow 2.81%. So we're going to have to pretty much evaluate the two functions. One of them is the amount after time, and we start at the 14,204.1, and we multiply that by 1.0095. This is the checking account after a certain amount of years. The other one is going to be also 14,204.1, but that growth is going to be 1.0281 T. Since this one requires you to open a new 5-year, the only way to accurately look at these two is by putting in 5 into either one. So if I opened a checking account and just let it sit, or if I put a CD in. And what we want to see is what's the difference going to be in how much prices we've earned there.